Okay, let's try this again. We're going to talk about exponentiation. Going to use definitions, postulates, notions, and propositions to prove theorems. This is very similar to what you'll be doing in a discrete class in some ways, and also in a linear algebra or in higher geometry. We do a lot of this. We're going to identify the axis of symmetry of a shape or transformation. As a reminder, the NES test prep is number 5 is going to be Thursday, November 2nd. And the textbook homework that's due November 9th is listed here. And we have student work presentations on Thursday, November 9th. All right, so let's talk about whole number exponents. We're going to talk about this in a way that you guys already are familiar with, and then we're going to see if we can expand that or help to grow that knowledge in a little bit different way. It might also help when you go to explain these to students. So first, let's start with a definition. Let Z be any complex number, and let N be any positive integer. So we're talking not just about real numbers. And I know that for you guys, most of what you've done has been real numbers, but we're going to include complex numbers because the reality is students will see complex numbers. The expression Zn is defined by the product of Z times Z times Z, etc., n times. So there are n factors of Z. Here, we're just talking about complex numbers, but remember that all real numbers are included in complex numbers. So by taking what we know to be true about real numbers, and not everything is true when we go to complex numbers, but those things that are, we want to know because that gives us some similarities and we're comfortable with it. So we refer to Z as the base and N as the exponent, very similar to when you would use maybe B and N. I tell students that the rules for exponents are shortcuts. That's really what they are. If they forget the rules, they can always go back to the definition. Okay, so if they forget them, they can always go back. And let's be clear what this means. This means x, say x squared times x cubed is really x times x times x times x times x. Okay. That's really all it is. And so that would equal x to the 5th power. If, again, when we know the shortcuts, we can just go, well, x raised to the power of 2 plus 3. But that's a shortcut. We can always rely on this. And I always say that you really shouldn't learn shortcuts before you learn the understanding, because that's happened to a lot of students. And then when that understanding is supposed to grow, it can't grow because they don't actually have the understanding. And then they end up floundering and then they give up. And that's not what we want. We don't want our students to give up. So this applies all the way around. So x squared to the 3rd power is really x squared times x squared times x squared, which is really x times x times x times x times x times x. So x to the 6th power. Again, we could have just said, well, x squared times, or raised to the 3rd power is the same as x to the 2 times 3. This works with division. X to the 5th power over x to the 7 means there are 5 x's on top, 5 x's down below, and we can filter off our ones. And genuinely, will that work? Let's see. Maybe not. And then, oh no, it doesn't show up very well. It's not going to work. Okay. And filter off the ones, and we're going to have that is 1 over x squared. So always a nice thing to see. So, oh, that's better. Let's try that. Maybe I can do this. Or not. Nope, guess not. All right, that's fine. Really doesn't make a whole lot of difference. You guys are familiar with this. X times y to the third power is x times y times x times y times x times y, which you could write as, since they're all multiplication, you could put x times x times x times y times y times y. So you'd have x to the third power, y to the third power. So let's look at some power functions. This is a good place to start, even when looking at more complex polynomials. First, even degree polynomials are smiles. If they're positive, they're a smile. If they're negative, they're a frown. And yes, the first one you see is an x squared. The next one is an x to the fourth power, x to the sixth power, and so on. And all it really does is it looks like that it is sitting on the x-axis longer. And that's often how I describe it to my students in college algebra, or any algebra, actually. I talk about it and say, well, it's just sitting there longer. There's a little bit more happening. We don't have to get into the details. There's just a little bit more happening. If we want to explore the details, we'd have to know the function and actually do the work. But we don't need to when we're just looking like this. What else? So then we have odd functions, odd degree powers. And all of these are the same. Genuinely, if it's a first degree polynomial, it works and it is a line, which is a first degree polynomial. And if it's positive, it's going up. If it's negative, it's going down. This is a cube root. Again, same direction. End behavior is actually the same in either case. Both of these fall on the left and rise on the right. Fall on the left, rise on the right. Assuming these are positive, right? This is what's happening. Over here, this is a fifth degree, and it's doing the same thing. Albeit it's sitting there a little bit longer. So we're going to kind of look at these, and I'm going to just kind of put up the question. This is one of the questions. Consider the graph y equals x to the fourth and y equals x to the sixth. X is a real variable, so I'm not even dealing with complex yet. I'm just saying it's a real number. At what value of x do the graphs intersect? Well, put the two functions equal to each other, find out where they intersect. On what interval is x to the fourth greater than x to the sixth? And on what interval is x to the sixth greater than x to the fourth? And here's the key: give convincing explanations for your answers. Why? Why do they intersect when we put them together? Why is that where the graphs intersect? And generalize that previous exercise to the graphs of y to the x of n and y to the x of m, where m and n are positive integers. And you can decide that m is greater than n. Or you could decide the other way. As long as you define it and explain it and generalize it, that's what I'm asking for. And this is one of those that we'll kind of talk through on Tuesday. All right, we're going to keep going. Integer exponents. So integer exponents are fairly straightforward. We've already talked about whole numbers, so we're just going to focus on the zero and on negative exponents. And in this case, we have z as a non-zero complex number, and n is a positive integer. So negative n would be negative. We define z to the power of 0 to equal 1, and z to the power of 1 over n to equal 1 over zn. And we wonder, students often, I get this all the time, and I don't just get this I get this in algebra classes, college mathematics classes. They struggle with this. How could you demonstrate to a student why z to the power of 0 is equal to 1. Consider how you might do that. And after I upload these slides, I will put this one on my tablet where I can actually write and maybe show one of the things I do to help students understand this. And let me say that the thing I do will actually help with this one too. How could you demonstrate to a student why z to the negative n is 1 over zn? And I'll show you what I do, and that may help. It appears I can't write on this particular device the way I wanted to, but that's okay. We're going to get through this, and then we'll go from there. Looking at properties of exponents, z to the power of a times z to the power of b is equal to z equals a plus b. Now, we were given the case that a is positive and b is positive in the last section. We used a special case where a is less than 0, less than or equal to 0, and b is greater than or equal to 0 to create the rule for z to the negative power. Now, to prove that case in general with different values of a, b, it's kind of a quotient rule, but we use cases. So let's kind of walk through those real quick. So the quotient rule says z to the power of a over z to the power of b is equal to z to the power of a minus b. Well, suppose a equaled b. If a equals b, you have z to the a over z to the b, which is equal to z to the power of a over z to the power of a. Well, that's equivalently 1, right? Anything over itself is 1. But if we look at it from the other side, from the right side here, we know that it's equivalently z to the a minus b. But a and b are equal, so that's equivalently z to the a minus a, which is equivalently z to the power of 0, which is equal to 1. So this isn't the way I show it to students, but this is more mathematically accurate. Let's look at another example. We have z to the power of a over b, and z is equal to a minus b. We already know that. So suppose a is greater than b. Well, since a and b are whole numbers, a equals b plus some n. For some whole number n, we've already said a is greater than b, so a is equal to b plus n. So a to the b, z to the a over z to the b is z to the b plus n. Again, we've said it's equal to that. Over z to the b. Well, z to the b and z to the b is equivalently 1. So again, that filters off, and we have 1 times z to the n, which is just z to the n. Since a equals b plus some n, and n equals a minus b, z to the a over b, this side, is equal to this side, but now we're replacing n back with what we know it's equal to, a plus b. So z is equal to a minus b. This was going with a is greater than b. Now let's look at the same thing. Wait, this is still the same. Nope, this is the reverse. Darn, I should have done this one in steps. All right, z to the a over z to the b is z to the a minus b, and we're going to suppose a is less than b. A and b are whole numbers. B, because it's greater, is equal to a plus some n. That's a whole number. Z to the a over z to the b is equal to z to the a over z to the a plus n, which would be z to the a over z to the a times z to the n. Z to the a over z to the a is equivalently 1. So we have 1 up top. We have 1 times z to the n is z to the n, which is z to the negative n. Since b is equal to a plus n, n must be equal to b minus a. Thus, z to the ab, z to the a over z to the b is equal to negative z to the b minus a. All I did was factor it, right? So I could have get it reversed so I can put a minus b. So z to the negative quantity of b minus a is equivalent to z to the a minus b. The other properties of exponents can be proven for zero exponents and negative exponents by breaking things into cases in similar ways. So we did the quotient, which I often think is the hardest for students to grasp, but you could do it with the addition and with the multiplication and the power, not addition. I mean, it's an additive property, but it is the addition rule. All right, so some of the questions from this topic are right here. You're exploring x to n, where n's a positive integer. And now recall the graphs for negative integer exponents. And by hand, you're asked to graph a few. And then use non-real zero numbers as your domain. So again, you're staying in the reals. Check your answer using something like Desmos. And consider the function where n is a negative integer and make conjecture on the values of the limit of x as it approaches infinity. Also, from the left side as it approaches infinity, and then as it approaches 0, from the right and from the left. Or as it approaches infinity and as it approaches negative infinity, as it approaches 0 from the right and 0 from the left. And then what's the range of f? This function, f of x, is equal to x to the power of n. And how does this exercise help in understanding why 0 to n is not defined if n is a negative integer? And I think this will come out as you look at these here. It may actually be apparent right from the beginning, but I think when you're doing C and you talk about the range is where this piece here is going to come out, and you'll be like, oh. And again, we're not going to say clearly, but we're going to actually explain what's happening and why that will now hold true. And then in 2, you're going to consider mathematical notation that arises with negative exponents. And you're going to write this complex number, 7 plus the square root of 2, the quantity of 7 plus the square root of 2 to the power of -1 as a fraction, and then try to write it in the form of a plus b times the square root of 2, where a and b are rationals. And the reality is, you know this procedure. You guys like to do it even when it's unnecessary. But it's necessary in this case, and you normally learned it under the thing called rationalizing the denominator, because they don't like seeing square roots in your denominator. So you're going to get to rationalize the denominator. You're going to write 7 plus the square root of 2 to the power of -2 in the same form where they're rational. So you'll rationalize again. And then you're going to do it with an imaginary number. The quantity of 4 plus 13i. And you'll do it as a to -1 power, and then you'll do it the same for -2 power. And you're going to discuss how the parts from doing the square of this complex number with the square root of 2 and this complex number with the 13i, and how they're very similar. And I want you to explain it as precisely as you can, the specifics of what makes those so similar. Okay, so kind of a review idea. What are the properties of exponents? I'm kind of taking for granted that you guys have used these relatively recently, but maybe you haven't, so we should discuss them. Here's my little, I don't know, explanation page. It shows the product rule, a to the x plus a times a to the y. The bases are the same, so it's a to the x plus y. division, and I'm just using the division symbol here because we don't often see this when we're using the quotient rule, so I thought it was appropriate to use now. A to the power of x divided by a to the power of y is, since the bases are the same, equivalently a to the x minus y. A to the x raised to the power of y is equal to a to the power of xy. And the power of the product rule, a times b raised to the power of x is equal to a to the power of x times b to the power of x. And the power of a fraction rule, a over b to the power of x is a to the x over b to the power of x. And the zero exponent rule, which we've already talked about, a to 0 equals 1. And the negative exponent rule, a to a negative x is equal to 1 over a to the x. So rational exponents. Let r be a real number and q be a positive integer. R possesses multiple qth roots whenever r is not equal to 0 and q is greater than or equal to 2. However, we feel a need to distinguish we feel the need to pick a distinguished root from among those roots. This is driven by two goals. When we think in terms of what we use in our day-to-day, we want real numbers if possible. If r is positive, we want our root to be positive. We would like to pick a root whose argument has the smallest possible absolute value. I should note that, let's see, not yet. Let r be a positive real number. Let w be a rational number, where w is equal to p over q. It's a rational number. And q is greater than or equal to 0. Then r to the w, this rational number, is equal to r to the 1 over q to the power of p. Right? W is equal to pq, so this would give us, if we multiplied them, r to the 1 over q would be times p would be raised to the p would be r to the p over q. And we're going to turn that into a radical. So we have the qth root of r raised to the power of p. And then that p, so the top number, ends up on our root. And note, we haven't defined r to the 1 over q for q less than or equal to 0. Have you ever heard of the 0th root or the negative second root? We don't normally do that. Now, we're not saying p can't be less than 0. We're saying that the 1 over q is not less than 0. So you can evaluate this following expression. As you do, think about how you would explain the problem to students. So this is the negative 64 to the 1/3 power raised to the second power, to the negative second power. And then the negative 64, the third root of the negative 64 raised to the square. And you have to figure out, okay, so what am I doing to the negative square? So if you raise that 64 to the negative square, you would have 1 over 64 squared, negative 1 over 64 squared, all raised to the third, to the cube root of 1 over 64. And then you can figure out what 64 is, the cube root of 64. I always think of it as doing it the inside first. So that cube root, I would say, okay, negative 64 is the cube root of, or the cube root of negative 64 is negative 4. Negative 4 times negative 4 times negative 4 is going to give me negative 64. And then to that result, I am squaring it, which is going to give me a, or no, I'm not squaring it. I am negative squaring it, so it becomes 1 over the -4, which becomes, well, 1 squared, doesn't matter, or 1 over the -4 squared, and that becomes 1 over 16. So that is 1/16. I'll probably do one writing this one out too, just so you guys have it, because talking through it is kind of difficult. How do we know that we get the same number if we write W as some other fraction? Say W is S over T. Well, here's an example. How can we show that 7 to the 4/10 power is equal to 7 to the 6/15 power? Using roots. And can we generalize if P, Q, S, and T are integers with Q and T both greater than 0, if P times T equals Q times S, and if R is any non-negative real number? Then R to the PQ is equal to R to the ST. So generalizing this is actually question 13. So I do want you to consider it. And is it necessarily true? And then discuss it. And generously, I thought, well, let me give you a little sketch, except not a picture sketch, some sketch of the work. So suppose R is a real negative number, because that's what it says here, negative real number. We were talking about non-negative initially, but let's be clear. Let's find out what it is for negative. That's what 13 is asking. So we're saying R is a real negative number, and we let P, Q, S, T be integers with Q and T greater than 0, such that PT equals QS. So we get to use all of that. And then we can say, well, if PT equals QS, then we can divide this side by Q and this side by T. So we end up with P over Q is equal to S over T. If R is to the power of P over Q equaling R to the power of S over T, this is R to the Qth root of R to the power of P, which is equal to the Tth root of R to the power of S. Thus, it is necessarily true that the Qth root of R to the power of P is equal to the Tth root of R to the power of S. So that's kind of an outline that I would use to prove it, to show it, and then discuss why this is true, right? Is it necessarily true? Yes, I'm showing you that it is, and then you're going to get to talk about it. Okay, so that's all the homework or the slides I'm going to give for this time. And then I will do another one that just has these worked out on my tablet, and I'll do that as a second video. All right, you guys, I hope you get a chance to watch this before Tuesday's class. Come on.